are looking at geology from the scientific, the technological, but also from the economical point of view, as mentioned there in ore deposit. So what are we going to do today? Look at the same type of objectives, but we're going to do it beyond Earth and look at resources outside our planet and how they can enable exploration, but at the same time usher us into the new space economy. And so let's start, hopefully by the end of this talk, I think the group can get together and maybe revise its charter and add at the very end of its objectives that they will do all this on Earth and beyond. So hopefully I can convince you about doing that. So let's start with a place that we are all familiar with, our Earth. Earth, where resources have been the driving force behind exploration, but also the means to do so. And they have become part of, integral part of our lives, our economy, and our society. And also to see how is that what we have learned from centuries of exploration can help us as we start going beyond and looking for resources outside. Corey, maybe if you can mute, I can hear some sounds there. Just mute everybody, probably. Yeah, I think it's okay now. All right. Can you hear me still? Okay. Are you there, Corey? Maybe I'm.
Yes, just fine.
All right, good, good. So let's, instead of actually start going to space in the future, let's actually first go back in time, way back in time to 120,000 BC to meet our ancestors, the Homo sapiens, that as a result of environmental degradation and droughts and population growth, they left their birthplace in Africa towards other parts of the continent, to Europe, to Asia, looking for basic elements for survival, basically water and food. And in the process, they develop technology like food preservation and controlling fire, and develop tools to live in ever more extreme environments. Then about 15,000 years ago, when they crossed into Americas, the first economic revolution took place. That's agriculture, that started allowing humans to settle, and first in small villages, towns, cities, and eventually entire civilizations. Then in the 15th century was about crossing the oceans, looking for not necessarily elements for survival. It was for trade, silk, spices, gold, silver. And then in the 18th century, it was about searching for oil all over the place. This was the second revolution, the Industrial Revolution, an element that is still our main source of energy. In the last 20 or so years, it has been still the look for more resources, this time for those very rare elements on the periodic table that are now part of our phones, the cars that we drive every day, and that are driving the renewable energy industry, the rare earths. So as you can see, resources on Earth have allowed us to explore every corner of our planet, have allowed us to live off the land in ever more extreme environments, and they have become the main engine of our technological society. So what happened when we started exploring beyond Earth? Well, one can say that it was a story of survival, but this time it was the competition between the two superpowers of the day, the Soviet Union and the United States, trying to reach the higher ground and to show their technological prowess. Once the race was over in 1969, we continued. We figured out that if we could send probes, and we have done that to collect scientific information for every planet of the solar system and beyond. But something happened on our way to heaven. I mean, we realized that space had value, that it could be useful to us, and without noticing it, we have incorporated space into our everyday activities. This all started with the very first privately sponsored satellite, the Telstar-1 in 1962, the first time we established communications between Europe and the United States, real time. And what Telstar did was to explore and exploit the very first resource in space. And that is simply the view from above. So what this has given us is weather forecasting, global communications, a GPS system that can allow us to locate every point on the surface of the Earth with extreme accuracy. And also, it's not only the first use of resources, but the only commercial use of space at the moment. Communication satellites is a $380 billion a year business that is predicted to grow by several studies to the trillions in 30 years. Now, in order to grow to those levels, we're going to have to actually use more resources than just the view from above. And as we know, there's unlimited amount of resources beyond our planet and in a whole solar system. But here is important to make a definition. And I don't need to tell this to this group because they know it extremely well, but I'm just going to put it into context to something that you're familiar with. We know that when we speak about a resource, it only has value by its utilization. If we don't utilize that resource, it's only a matter of scientific interest or of curiosity. And there are 3 steps that one has to fulfill if you're going to extract resources on Earth or any other place in the universe. And these 3 steps are the following. One, you have to have a recoverable resource. That means you know a resource with enough geological, technological, engineering, economic, legal, environmental certainty that you know you can go after it. In the mining and oil and gas industry, that's called a proven reserve. Then we need to have a technology to recover it. And third, as important, if not more important than this, you have to have a customer. If there's no demand, you can have as many resources anywhere. It doesn't make sense. They're not good for anything. So what I'm going to do in my talk, I'm going to go through these 3 steps. I'm going to first identify the resources beyond Earth. Then we're going to look at technologies that we are developing to start recovering it. And then we're going to see what the demand is for this and who's the customer. So let's begin by looking at what resources are there beyond just the view from above. The moment we cross our atmosphere, we're going to enter into low Earth orbit at a place that we can experiment conditions that are hard to replicate on Earth. That's ultra high vacuum and low gravity. And what this allows you to do is to come up with products under very unique conditions that at some point you can bring down to Earth or utilize in space. In fact, some of the companies that are now working in low Earth orbit are developing very advanced optical fiber for very ultra high bandwidth in microgravity conditions that at some point we can bring down to Earth. The other thing that we have plenty of is sunlight and solar power. That's good not only to power spacecraft, but imagine in the future that you can collect all that energy in orbit and then beam it down to Earth in microwaves or lasers to individual points on Earth. You can have energy, plenty of it, 24/7 without worrying about clouds or about plastering the whole planet with solar panels. So this would be a good use of sunlight. All of this are the so-called intangible resources. That means you don't necessarily mine these things, but still are going to be very important in order of the benefit that we can get from it. If you want more concrete elements, then we're going to have to start traveling and heading towards our nearest celestial neighbor. So let's go to the moon. The moon that when we got there, there was not much hope of anything that could be of use. In fact, if you look at the recordings from the Apollo 11, of the first words that the second man on the moon said when he stepped out of the lunar lander, he looked around and he said, "Gosh, this is magnificent desolation. There's nothing here that can be of use. There's no air to breathe. There's no water to drink. There's no plants, no wood, no cows, nothing that can be used to humans." And in fact, that was the feeling back then, but our view of the moon has changed radically since then as a result of several satellites going around that give us remote sensing data. We have 380 kilograms of rocks that were brought from Apollo and a few grams from the robotic missions from the Soviets. And that has given us a view that has transformed the view of the moon as magnificent desolation to a place that is full of resources that can be utilized in the future. So let's see what resources are there on our moon. So first, our moon has 2 phases. The near side, the one that we see almost every night, and the far side. This is the place that we don't see, although there's plenty of light, even though some people call it the dark side. There's plenty of 2 weeks of sunlight, 2 weeks of darkness. And but because the near side, because the moon is tidally locked to the Earth, we only see one side. And it is that side, in the one that we can communicate and the one that we can see, in which we have done most of the exploration. That's most of the American and Soviet and Russian missions have been done there. Also, China has landed in a place. And the far side has been forgotten just because it's hard to get there and relay all the communications. Until the beginning of last year, when China landed in a very important part of that part of the moon. As you can see it without even pointing out, there's this section that is a little bit darker than the rest. That is the South Pole Aitken Basin, one of the largest impacts in the solar system that exposed the mantle and brought the material to the surface on that side of the moon. And as you will see, the reason they landed there is because this region is very important scientifically, but also in terms of resources. So in terms of resources that are common to both sides, even though there's not an atmosphere, there's still plenty of oxygen on the moon. 45% of the moon's oxygen is just tied to the rocks, these oxidized rocks that we have over there. 21% is silicon, a very important element. And that's where the common elements end. If we want to look at other type of elements, metals and non-metals and other things like that, then we have to look a little bit into the geology of the moon. And without going too much into geological details, the first thing that stands out is dark spots and bright spots. And the dark ones are called the maria. This is a volcanic material, it's basaltic. It's basaltic material that was exposed and filled all the impact craters on that side. And it constituted about 23 or 24% of the moon. It was called Maria by Kepler because he thought it was oceans, and that's why he called it that way. The other part is the Terra. About 83% of the moon is the primordial crust of the moon that has been like that for billions of years. It's an orthocetic material. And here is where nature has given us an opportunity to see where the most important resources are because they're mostly concentrated on the near side. Let's start by looking at just iron, such an important element. If you look at it, it's up to 14% of iron on the near side, concentrated on the mare, on ferrous oxide and ilmenite, primary minerals. But interesting enough, significant amounts exist on that region where the Chinese landed last year on the South Pole Aitken Basin. Titanium, such an important element for the aerospace industry, again, concentrated on the near side in large concentrations with a little bit on the far side. Now, the moon has this creepy side to it, but creep with a K. That stands for potassium, rare earth elements, and phosphorus. This is elements that concentrated on a part of the moon that stayed as a liquid when the rest was crystallizing. And that's where you have your uncompatible elements and you have your heat producing elements such as uranium and thorium. In fact, this is a map of thorium, but this is the region when you find the concentrations of rare earth, potassium, phosphorus, and radioactive elements. Now on Earth, if you want to go after any of these elements, you're going to have to start using dynamite and breaking rock and pulverizing the material so that you can process it. Luckily, the nature has also helped us on that quite a lot, because for billions of years, the moon has been bombarded first by large asteroids, then comets and micrometeorites and meteorites. And in the process of hitting the hard rock, the surface, what they have done with these impacts is that they have completely pulverized the surface of the moon into this very fine dust in the order of 60 to 70 microns that you can find all over the surface of the moon as a result of this impact. This is the so-called lunar regolith. And that is the reason why we see the footprints of the astronauts on the moon, and we don't see them walking on rocky material. So there's this very fine material, very loose in the first 10 to 30 centimeters, and then it becomes extremely dense. And it's constantly gardened. There's this process called gardening because it's constantly hit by micrometeorites, and you're mixing all these elements in the first 10 meters or so. Now, this fine dust is nothing like you find on Earth. If you go to a riverbed or the sandy beach, you find nicely rounded rocks because they've been eroded by water and wind and all that. Contrary to that, on the moon, it's very different. These are jagged edge, extremely abrasive, glassy material, agglutinates that have been formed by impacts and heat on the surface of the moon. And so we're going to have to watch out for that because these things can eat up any mechanical system, can eat your lungs if you breathe them. And so they're going to be quite a challenge to deal with them. So even though we have pulverized material to work on right away, we're going to have to deal with it. The other thing that has happened is that the moon has been bombarded by billions of years by solar wind. These are ions and particles. And because the moon doesn't have a magnetic field, they just get implanted on the soil, on the regolith. And what ends up happening is you find particles that are important coming from the sun. This is material that is important in terms of resources like hydrogen and helium and nitrogen and carbon. The little carbon there is actually coming from the sun. And even you can find elements that are hard to find on Earth. In fact, one of the elements that have been found that in several orders of magnitudes higher on the moon than on Earth is this isotope of helium called helium-3. It's found in parts per billion, but it's an important element that has been suggested to be used at some point if we ever get to control fusion energy. Not fission, fusion. And the importance of it is that you can fuse two elements of helium, in the process producing energy and producing protons. So you produce electricity right away without having to go through the steam cycle, having to heat up steam and all that to produce electricity. And the most important thing about it is that the elements of the residues is helium, the stuff that you use on balloons for parties for kids. So it's a clean form of energy. If we ever can get control of fusion energy, this will be a process with no radioactive waste. Now, the other thing that happens with the regolith because of this implantation from the sun is that not only it's abrasive, but it gets electrostatically charged. You have this charged dust all over the place. We tried to do an experiment at School of Mines just to demonstrate this. And so what we did is just simulate the radiation from the sun with an electron gun. And we did that with 2 mounts of lunar simulant. The moment you turn it on, you can start seeing how the dust starts moving around, it starts levitating because it's electrostatically charged. And when you start interacting with it, if you're going to do that with excavators or tools, you also do this thing called tribo-charging. You start charging the material. In fact, it levitates. Every time you go from night to day, this thing levitates about 1 meter, and you're going to have to deal with that issue that you don't have here because there's no humidity over there, and that's why you don't settle this material. Fine. The other thing that resource that is so important to us that we look for everywhere we go is water. So how about water on the moon? Is there any water there? Well, at first the thought was there was no water at all. And the reason is because the moon has this property, this inclination of just 1.5 degrees with respect with the sun, not like the Earth. The Earth has like 23.5, and that's why you have the seasons and the like. Here, you're completely exposed to the sun. So when the moon is rotating around the Earth, the sun is completely illuminating all of its surface, not just one part of it. And so any hope to find water on the moon completely literally evaporates because there's a vacuum. There's also this movement on the moon called precession. It wobbles, the moon wobbles, and what happens, it exposes the north and the south pole, so everything is exposed to radiation. So again, this will tend to evaporate any water on the surface. However, scientists said, well, what about because of this very inclined angle of the sun on the poles, what if on the north of the south pole, there could be some very deep craters, so deep that they have never ever seen the light of the sun for billions of years. And what if ice from comets or asteroids or hydrated minerals end up in these permanently shadowed regions at a very cold temperatures, about 40 degrees Kelvin, and they may still be there. So several missions were sent in the 1990s, starting with Clementine, that used radar reflectivity, and the reflections indicated that there could be probably some presence of water ice. Then a very aptly called mission called Lunar Prospector used nuclear spectroscopy that detected hydrogen, not necessarily water, but very high levels of hydrogen. Then the Indians sent a mission with a infrared spectrometer, and again, giving you indication of water ice. And finally, the Lunar Reconnaissance Orbiter that's still going around the moon has confirmed that indeed it seems to be that signals are coming from ice. So what these missions did was to give us an idea of a couple of important resources. One is just purely location. They told us that indeed, both on the South Pole and the North Pole, there exist these regions of permanent darkness, the permanently shadowed regions. What these images are an integration of all the light on 6 months of lunar cycles. So you can tell what areas are exposed or not. The other important location is the rims of this crater that are usually called the peaks of eternal light. They were called like that by a French scientist in the 1800s, very romantic guy that gave him that name. But indeed, it's not eternal, but 90% of those regions experience light instead of the rest of the moon, which is 2 weeks of nighttime, 2 weeks of daylight. And so these are going to be key places where you want to have your base because you have power, you have communications, you have sunlight. And in fact, those are the places where the missions planned by the United States and the Europeans and others are going to go in 2024 and 2025. They're going to be on the rims of these permanently shadowed regions. And in the future, you can even think about beaming the light from there to the bottom of the craters. And we're going to take a look at this and utilize that energy to evaporate or sublimate the water so that you can utilize it. The other thing that it gave us, those missions, is that they identified places where we can go and touch. Like exploration geologists that you are, you don't just rely on remote sensing. You want to go and touch and drill and make sure that the resource is there. And that's exactly what a mission did by identifying for remote sensing that this could be a place where water could be found. So the ground truth mission that was planned was called LCROSS. And in this one, what it did is that there were two modules that separated. And the first one, the white one there, went in and just impacted the Cabellos crater. A big plume came out. And in that plume, the second spacecraft for 14 minutes, and also observatories from the ground, detected the presence of water, anywhere from 3 to 8%. And not just water, water mixed with all sorts of materials, from hydrogen sulfide and ammonia and methanol and mercury and magnesium, all sorts of things that are there because many asteroids have deposited these materials. So one would have to be you gotta have to be careful when you clean up this material, the water, because it has a lot of nasty elements, but these elements can also be resources. You gotta be as resourceful as possible. This is a place where you can get carbon that you cannot get anywhere else. So that's the presence of water. So what this has given us is a view that on the poles of the moon, there is water ice. Yes, in small amounts, like here in the South Pole, but 3% of what you would call the Arctic Circle is water ice contained on these permanently shadowed regions. Water that can be utilized for a variety of things, for propellant production, for human consumables, and the many other things that we use water for. Now, you may be also as geologists saying, well, how much water is that? Well, the estimates, and at this point, I'm talking inferred resources, the bottom of your JOR code, nothing proven. It's only one data point that we have, but the estimates from that in remote sensing is that we have between 100 to 1 billion metric tons of water per pole. Now, you would say, how much is this? Well, let's put it in Colorado units of measurements. It is about 2 to 3 Lake Dillons. So as you can imagine, this is not much water in terms of all the oceans and things that we have on Earth, but it's plenty of water for the many things that we want to do. I mean, the calculations are for hundreds and hundreds of years of propellant and human consumables. So even though it's a non-renewable resource, we're going to have to learn how to use it responsibly, but also it's going to be of much use when we start extracting it. So we have all these elements on the moon: volatiles, metals, rare earths, and the like. But let's keep going. And let's catch up with these amorphous rocks that are floating all over the solar system. These are the asteroids. It's asteroids that are from anywhere from a meter to the largest ones, which are dwarf planets like Ceres, about 1,000 kilometers. But most of them, except for Ceres and Vesta, are this oddly shaped material that was formed from the early solar system, and they are pretty homogeneous in terms of composition. The important ones is not necessarily the ones that we learn from high school, you know, this asteroid belt that is very nicely behaved between Mars and Jupiter. It's not that the case. I mean, they impact each other. There goes to instability. So these rocks end up everywhere in the solar system. And some of them end up caught up in orbits very close to the one that the Earth has around the sun. So very close to that. And those are called the near-Earth asteroids or near-Earth objects. And their importance is because they are near to us. You know, we can travel to them in months, and we can get to them and probably obtain their resources in the future. And what are the resources on these elements? These are the spectral type. These are classifications of about 20 of them, but 3 are the important ones in terms of what we can observe from the ground. First, they're type C. These are the carbonaceous ones, like Mathilde that we visited in the 1990s. Other than carbon, it also has up to 20% of water in terms of hydrated minerals. Then you got the S types, or the silicaceous or stony objects. And these ones have a nickel, they have iron, silicon, and a little bit of the platinum group metals. And finally, what is the mother lode in terms of metals is the metallic types, the M types. And these are objects that we have not been visited. So this is just an image that we have of one that we're going to visit in a couple more years, Psyche. And these are remnants of planets that differentiated. They were big enough that accumulated all the heavy metals on the center, and then they were hit by other impacts and they removed the crust, and all they were left is pure metals. You got nickel and iron and platinum and gold and all of those noble metals. Now, some people have a hard time memorizing this. I'm going to give you a tip of how to memorize these types. They go by CSM, Colorado School of Mines. So that's just a subliminal message and advertising in the middle of the talk. Now, we know a lot about these elements also from the thousands and thousands of meteorites that we have on Earth that we classified very similarly. We have the stonies and the stony irons and the iron ones. And so we know about their properties that is expected that are quite homogeneous in bodies that didn't differentiate. So those are the meteorites. So to all the moon elements, we can add all the types, the C and the S and the M's. If you go beyond that, then we can go all the way up to Mars. And in Mars, and its two moons, Phobos and Deimos, Mars has all of these elements, but it has plenty of water. You can even see it on the poles right there. But actually, it's plenty of water in terms of glaciers that are a meter or two in the mid-latitudes, and there's plenty of water there. And also, it has a carbon dioxide atmosphere. And the moment you have carbon, think about hydrocarbon, think about plastics, and everything else that we can utilize carbon for. And that's as far as I'm going to get in terms of identifying resources. This is where we think we can identify and extract in the next 30 or 40 years. Beyond that, there's moons of Saturn and Jupiter with plenty of resources, but that's just way out there from my point of view. And these are just natural resources. Believe it or not, there are human-made materials or resources in space already. And that's all the junk that we have sent for 60 years of sending rockets up there, bolts, nuts, and unspent rockets that are already there that we need to remove and might as well recycle them and extract the aluminum, the titanium, the chromium, all those important elements that we can utilize. We have spent a lot of money doing this. Why not utilize these elements for our use in space? And so here the question is, which space resource is more valuable? And if I were to do a survey among you and all your members, everybody will have their favorite ones. You know, somebody will go for the gold and somebody will go for the rare earth. But this is a tricky question. Is this on the near term, the medium term, or the very long term? Are these resources we want to bring back to Earth, or are these resources that we're going to use in space? Now, if you just do a quick calculation and analysis and you look at how many resources we have obtained on Earth and how thin we have gone in terms of its crust, there's still plenty of them on Earth. And its cost, even though it's going to start rising, still it's very low compared to actually getting them from space. It's not going to make any sense until we start digging too deep, spending too much power, and causing too much environmental degradation. And by the time we have infrastructure in space, that it will make sense to bring them to Earth. At this point, the idea is to use them in space. And the reason is the following. Out of the thousands of rockets that we have sent into space, all the materials that have gone out there has come from Earth. We depend 100% from our planet to launch rockets into Earth and all the human consumables and all the satellites and everything. And as we know from our experience on Earth, that's not an efficient, that is not a sustainable way to explore, because at some point it's going to limit us from how much stuff we can send out there. It's also a very energy intensive operation. And it's all because of this force called gravity that keeps us firmly on the ground on Earth, and it makes it so difficult and so expensive to get out from it. Just to give you an idea of any rocket that you send into space, I just put here the Saturn V that took us to the moon 51 years ago. But any rocket you see on a launch pad, 90% of that rocket is fuel. And that's fuel needed to launch the rest, the 10%, which also is the structures and the tubes and everything. So you're lucky if you can send 2 to 4% of a payload. This is an extremely inefficient way to transport things, but that's the only thing that we know. It's also very expensive. It costs about $4,000 a kilogram to send anything into low Earth orbit. If you want to go to the moon, that's $35,000. You want to go all the way to Mars, that's $300,000 a kilogram. And that's just material. If you want to send humans, multiply that by 10 or 50 because we are an expensive species and we have to stay alive and all of those things. This morning, I just happened to check the price of gold, multiply it by my weight, and I'm literally worth my weight in gold to send me just to low Earth orbit, let alone the moon and the rest. So this is a very expensive operation. You're going to say this is exponentially expensive. Yes, it's exponentially expensive because the equation that governs rockets is exponential. If you want to go from point A to point B, from Earth to the moon, the amount of mass that you have to bring as propellant goes up exponentially. And so that's what makes it so expensive and so hard. And this is very inefficient. This is not the way that we do things here on Earth. If I want to go from Denver to New York City, I don't bring with me all the fuel that I need to get there and then to come back, or all the food and the drinks, and let alone all the chips that you need in order to get there. No, I stop on gas stations, I stop on convenience stores, and that's the way they operate. Same thing's gonna have to happen in space. We cannot be sending everything from Earth. So when the question is which space resource is more valuable, the answer to this is those that will make us live off the land, that we don't have to carry everything with it, that we can survive on the moon or Mars or even in low Earth orbit. This is what we call in this field, in a very fancy term, in situ resource utilization, that we can utilize the resources on site. And so when you look at all these other elements and all these complex things out there, the one that stands out is the same one that we humans go after everywhere we go. Simple, good old water. Water, because water is not only good for humans to drink, and maybe you can separate the oxygen and breathe it and grow plants and protect yourself against radiation and take an occasional shower every once in a while, but also water that you can split into hydrogen and oxygen. Hydrogen and oxygen, that is the most energetic fuel that is known for rockets. And so if you have that capability to find your water on the moon, not only you can use it there, you can split it into hydrogen and oxygen and use it for any rocket that is going to launch from the moon without having to bring that fuel to the moon. Not only that, if you export that from a place with a much lower gravity than Earth, it becomes even less expensive to send something to low Earth orbit and put it there on a fuel depot than to send it from Earth. And then you can start putting fuel depots in different orbits, key orbits around the moon and Earth. And with this, you start creating a propellant refueling network. And just like on Earth, once you have that capability, then you start lowering the transportation costs. Now, instead of sending rockets and just getting rid of them, now you can refuel them and keep them for years at a time. You can start refueling satellites. You can even bring water from asteroids and deposit it on these fuel depots. And the moment you lower the transportation, you open up this to not just a few countries or a few humans that can go all sorts of commercial activity. So in a way, think about water as the oil of space, because that's going to open up all sorts of opportunities once you can get it from the moon or asteroids and put it into these fuel depots. And just to give you an idea of some of the studies in terms of cost that have been estimated, if you can obtain the water from the moon and then ship it to satellites in geosynchronous orbits, you know, you can have an advantage of about a 1/4x on the cost. If you want to send fuel to the Lunar Gateway, it's a station that is going to go around the moon, you have savings of 2x. If you want to just have things on the surface of the moon, you can get it 3 times cheaper than sending it from Earth. If you want to have fuel going back and forth for a spacecraft from the Gateway to the moon, it's about 70 times less because you don't need to bring it. And if you want to go to Mars, it's about 3 times cheaper. So finally, you can make this dream of going to Mars feasible, because right now it's impossible with any budget from any country that you can imagine to send all the fuel way up there and then to get them back. So that gives you an idea of the power of water in space. The other thing that would come next is just the use of the regolith itself. You can do construction, so you don't have to bring your bricks and mortar. You can do additive manufacturing. After that, metals for tools, spare parts. Again, you can use them whenever you need them instead of having to wait for somebody to launch it from Earth, so you reduce the risk. And so those are the things that we see in the horizon. Now, in terms of water and this first phase of prospecting or exploration, like I mentioned, we don't know much about it right now. So we need to start taking this from inferred resources to more measured or proven reserves. Because right now, we don't know if the water is snow, would be great, 100% water, we just go and collect it, or it could be dirty ice, or it could be ice mixed with regolith, just 4% of it, and we have to extract it somehow. So we're gonna have to determine that. And in fact, that's what's been happening. That's what you're gonna see happening in the next 2 to 5 years, a very ambitious campaign by the United States and other countries to go after ice that has been detected, but for actually ground truth. So the campaign will involve a variety of objects. You're gonna have ground truth missions, low cost ones, to just go and see what's in there on the first few years. Impactors, several of them, just to hit it and start seeing how's the water, what is the concentration, what is the distribution, what other elements are there, tether sensors from landers, and eventually the most costly ones is rovers and samplers that you can start just drilling every few feet to really determine how your resource is distributed and in what shape it is. So that's going to be the first phase in the first few years. And then comes, from those three elements that I mentioned, I mentioned the recoverable resource. The next one is, what is the technology that we're developing to recover it? Obviously, this is a chicken and egg problem because we need to know the resources so that we know what technology to use and vice versa. But one has to start foreseeing what's in there in order to get ready for it. So in terms of this is where the space mining term comes in, the technology that will be needed. As you all know, because you're experts, we have been very successful on mining on Earth because we have 4 important things. We have been designing the systems under the only gravity that we know. We have been designing it under the environment and under temperature or the pressure, the humidity, whatever we have here. We have plenty of labor and we have plenty of power. But if you start going to the moon, the lunar surface or Mars, none of these things will be true. You're gonna be acting on 1/6 or 1/3 gravity. You're gonna be acting on extreme temperatures, on a vacuum. As you can see from the upper picture, not much labor there, and power, whatever you have available, solar power or nuclear power that you can bring with you. So you're gonna have to start adjusting to a completely different environment. So what has been happening in the last 20 years is that we started by trying to imitate the type of systems that we have on Earth and try to replicate on the moon. That's all we know. And so we started looking at the type of big systems that we use on Earth and try to reduce them for the type of needs that we have on Earth in terms of bucket wheels, bucket ladders, backhoes, and all sorts of things that can be adjusted for the moon. But more and more, we have started thinking of completely new ways to do things that, yes, imitate some of the terrestrial system, but they are completely new. For example, for excavation, there's this contraption that you may not see going around on fields here on Earth, but this is a great excavator that can work under 1/6 gravity. It can work under a vacuum. There's no lubricants that can evaporate. It can operate on extreme temperatures. It can collect very abrasive material and move it around. And not only you can have a big one of this, you can have a swarm of this so they can work together. And if one goes down, you have another one. So you're looking for ways to survive in that type of environment. In terms of extraction, we don't generally drill for water on Earth. I mean, yeah, sometimes we do that, but most of the water you can get it from rivers and all sorts of places. Only places that you go for that is in Antarctica, in which you drill through ice so that you can get water for the people that live there. So similar things will be done here, the so-called Rodriguez well, in which you do boreholes with heaters, you heat up that soil, you sublimate the material, you cover it under a tent, and then you collect it on a cold trap, and that cold trap can move around from that place to wherever you're going to use it. Or you can use completely new systems, like something we call thermal mining, in which you can have reflectors on the top of the rims of those craters, beam it down to the surface, and with that you sublimate the water that has been there for eons, and then you can start utilizing it. And in fact, we already started doing some experiments to test these ideas. And so what we have done to simulate this, the tent and the different cold traps, is first what we have done is replicate the lunar environment. So how do we do that? We use vacuum chambers. And also we try to simulate the material. So we have learned from the material that has been brought from the moon, and we have done simulants in which we combine both regolith and granular ice, which is what we think is going to be there, but we also do other types of simulants. And also what we do is we expose them to the same radiation that you will get if you put a solar collector there, which is practically the radiation that you get from the sun on Earth or the moon, about 1.3 kilowatts per meter. And so here's an experiment in which we did it on a vacuum, did it with this simulant, and we just apply the amount of radiation that you will get from the sun. So what you will see here in a few seconds is about an hour worth of test in which the moment you turn on the lamp, you don't see anything because things are sublimating, but you're going to start seeing the soil house being now collapsing. And when it collapses, you can see how much you extracted, but also how you affected the soil by doing that. You can insulate it or change it. So we've been doing those type of experiments. Now, these are the experiments that we have done. In terms of what's coming in the horizon, in terms of extraction of resources, just this last July, there was a mission from the US that departed, the Mars 2020 mission. It will be there by next year. And it's going to extract the first resource from another planetary body. It's going to take the carbon dioxide from the atmosphere, go through a fuel cell, and it's going to give us oxygen. For the first time, extracting oxygen that can be used for breathing or for propellant. For the moon, by 2023 or 24, there's a mission that will go to the poles of the moon, and it's going to go down to the permanently shadowed regions. There it's going to start drilling, and in the process of drilling, it's going to start sublimating the ice that is going to be cold trapped, obtaining the precious liquid from a place that we thought it was bone dry just a few years ago. So that's what's on store right now in terms for the future. So we have looked at the recoverable resource, the technology. Now let's see if there's any customer. Who cares about this? So who is the customer? Well, about 20 years ago, it was basically NASA that was interested because that could give them some resources that they can use for just the missions there. But now that has now spilled over to other government agencies in the US. The USGS is extremely interested on this and is trying to apply its expertise that it has on Earth and apply that to space resources. The Department of Commerce, seeing that commercial activities are going to start happening, has created a space administration within the Department of Commerce that is going to start now regulating and trying to see how they can control all the commercial activity that is going to be happening. And it's not only the American Space Agency. At this point, is NASA, is the Russians, is the Europeans, is the Canadians, is the Indians, the Japanese, the South Koreans, the Chinese, the UAE, the Australian, even the tiny country of Luxembourg has invested heavily on space resources because they see it as their next great investment, as they invested in the 1990s on telecommunication satellites. And it's not only the government, it's the large aerospace companies that are interested, like United Launch Alliance or Lockheed Martin, that are now designing the rockets to be used with hydrogen and oxygen. Again, already seeing how they can refuel in space. And also companies like Boeing and Northrop Grumman that are designing the fuel depots that are going to be used in the space between the Earth and the moon. And in not only the traditional aerospace companies, the new space companies like SpaceX, that is looking at going not just to Mars, but they're planning to be on the moon in a couple of years as part of the many companies, almost 13 companies that have gotten commercial contracts from NASA to be there. Blue Origin, that is also using a lander using hydrogen and oxygen. And not just the aerospace companies, is the small, medium, and large companies, some of them that have done work terrestrially, that are positioning themselves in all of the steps of the value chain. Who's going to prospect? Who's going to do drills, excavation, separation, purification, and all the infrastructure, power, telecommunications, transport. Names that probably you may be familiar with, like Schlumberger or Caterpillar, are positioning themselves to be part of this identification and exploration of space resources. Seeing the international and the government and the private industry interest, the School of Mines decided that we also needed to add the academic component. It was about time to start teaching the generation of engineers that are going to be dealing with this. And so at the school, we have been dealing with space resources for 20 years. We were the very first center that started looking at this. But 2 years ago, we sensed that it was the time to create an academic program. And so we created the Space Resources Program, the very first one on the world, educating not just scientists and engineers, but economists, entrepreneurs, and policymakers in the field of space resources. As you know, as experts on terrestrial resources, you have to know about not just the best technology to extract them, but is it economic or not? Is it legal? Is it worth actually going there? And so we have created different offerings, certificates, which has 12 credit hours, Masters of Science, and even PhDs on this field. And the moment we launched this program, the interest was from all over the world. So what we had to do is to do it in an online way, just like we're doing here via online. And that's why we started creating the first fully online program at School of Mines. So every course that we teach, you can go online, watch recordings or discussion boards, but also we get into conversations like this every week. A class yesterday using this medium. And so what this, and the reason we also do Zoom and not just online is because we can be in touch with the students and the students can network among themselves, because these are people that are going to be working on this field from many points of view. So we have 2 sessions, one in the evenings, one in the mornings, and we get all these people together. And this has allowed us to have students from all over the world. We have people from 5 continents, from 18 countries, from 4 space agencies. We have professionals from scientists, engineers, policy analysts, entrepreneurs, investors, even lawyers, and from all sorts of industries: aerospace, mining, metals, oil and gas, chemical, computer science. Right now we have more than 100 students in the program. And so you can sense that the interest on this field is growing in all aspects. And talking about lawyers, the last question you may have is that this is all great. You know, there's a lot of interest internationally. There's private industry. I may even get involved. But is this legal? I mean, can I just go and set up shop there and start extracting my ice and start selling it and become a trillionaire? Are there any rules about this? And this is important because, as you know from your JOR code, there's all these modifying factors, and no mining company will touch something that is illegal. And so on this area, there's not much to go around. There's the Outer Space Treaty that was signed in 1967, in which more than 100 companies signed it, at a time where only the United States and the Soviet Union were doing this. So most of the countries signed because they said, well, there's no use, there's no need to go to space other than these 2 countries that are just going there for their own selfish reasons. But this Outer Space Treaty was very clear in 2 articles. One, the exploration of space shall be the common province of all mankind, and it prohibits national sovereignty. That means no country can own the moon or asteroids or Mars or anything like that. You cannot do that. So it was very clear. Then a second treaty came in 1979, the Moon Treaty, that was a little bit more specific. And that was at a time when nations were realizing, well, you know, there's more to space than just going there to show off. And so less than 20 countries signed it, and none of the spacefaring nations, not the US, Russia, China, none of them signed it. So what has been happening is that when you try to go to these treaties and try to find out to see if you can make a claim or something, then the language becomes really fuzzy. You cannot really tell what's going on. And so what has happened is that countries are taking matters into their own hands, starting with the United States, that in 2015, both the Senate and the House passed the US Commercial Space Launch Competitive Act, in which very clearly states that any citizen engaged in commercial recovery of resources is entitled to those resources, to possess them, to own them, to transport them, to use it, and sell them. So if you have a company that is in US, you can go and do that. Luxembourg reacted the year after that in what became the first European nation to offer a legal framework. And now you're going to start seeing the United Arab Emirates and Russia doing the same thing. So at some point, other countries started getting together and saying, what about us? And so a group in the Netherlands got together, the Hague Space Resources Group, in 2017, made out of about 35 countries that are now debating how the world can take advantage of this without being left out. This could be another rush to go for resources, and some of them are going to be left out in the dark. So how can they participate and benefit from these resources? And after 3 years, this has gone up now to the United Nations that is debating this. So at the same time that we're moving technology and science, we're also moving the legal aspect that are going to have to coincide if we want to assure companies that this is a safe place to go and invest your money. So what I want to leave you with is that, space resources promise to give us an unprecedented amount of not just scientific information, but of further exploration to allow us to travel further, to stay longer on planetary bodies, but at the same time to increase commercial activity to truly bring space into the global economy. It will depend on all of us here on this planet, on this rock Earth, to learn from what we have done here on the past, the good things and the many bad things that we've done on Earth, and with that, go after resources beyond Earth in an effective, in a responsible, and a sustainable way. So with that, I'm going to open it for any questions that you might have.
Just a moment here. So I think I have everybody. I'll just unmute all. Yeah, I'll just do it here. All right. Thank you very much. That was an excellent presentation. I'm going to ask a couple prepared questions submitted by John DeDecker. And then if anybody else has any questions, I will try to figure out how to unmute everybody all at once. And won't have to worry about unmuting. All right. So you mentioned refueling depots, but in addition to that, what other infrastructure might be needed to be built before space resource extraction becomes profitable, realistic? Sorry, we can't hear you. There you go.
Yeah, just like on Earth, you're going to have all sorts of infrastructure. It's not just go there and drill. You're going to need power and communications and all that. So what's happening now is that even small companies are injecting themselves to provide power, like modular nuclear reactors, or just a company building a GPS system around the moon because you're going to need communications on the far side, the near side. You're going to need, other than power, solar power too, and all sorts of things. So there's a lot of opportunities for just creating the infrastructure that you need in order to conduct operations there. So there's the opportunity for many companies.
Could extraterrestrial extraction ever be independent of Earth-sourced materials? And if so, when?
Okay, so here's where I mentioned that once we start extracting the resources on the moon, yes, at the beginning, we're going to have to bring all the excavators and all sorts of things. And then they're going to start working on their own. And the idea is to have several of this so that if one goes wrong, then the other one takes over. At some point, you may have start manufacturing parts over there. You have metals and you have additive manufacturing. There's research going around, and we actually have some at School of Mines on how you can extract the metals and use it to make parts and wrenches and spare parts. So at some point, and once you have a base in which now you have humans interacting with robots, you may be independent of those type of things. Obviously, it may not be totally independent until decades into the future. Once people start saying maybe full machines are going to be able to be made, more intelligent machines. But at the beginning, the whole point is to lessen our dependence from Earth, at least lower the cost to get there.
Okay. You mentioned the treaties of 67 and 79, the Hague Space Resources Working Group. The question is, what kind of institution or organization will be required to ensure responsible extraction of and conflict avoidance over space resources? I guess rephrased, do you think those treaties are much more than pinky swears?
That's the question that everybody has. Who's going to enforce this? What's going to prevent, for example, not even resources, let alone there. As I mentioned, some of the most important resources location on the moon is to get there to those places where you have more than 90% of light. And there's very few of those because they're in very high terrain in the poles. So you can already start seeing that the US wants to get there, China wants to get there, because getting to those places is going to be key to set up your operations. And so who's going to prevent, okay, I'm here, how far away you are from there? These are the type of conversations that are starting to filter, not just to the Hague, but to the United Nations, and seeing, okay, there's going to be some standards of who's going to go, what's the claim, how much can I stay at a place? And if somebody violates that, it's just like any international treaty on Earth. It's just name and shame. If you can see it all the time, people, you know, fishing in places where they shouldn't be doing that, and the whole world and the United Nations turns to them and shame on you. And at some point, there's trade wars and all that. It's impossible to go and enforce unless you have a space force. And there we get into another tricky subject, which is the role of the military in all this, which is very interesting, because the moment you have commercial interests of the United States there, somebody has to protect them. And so now you recreate everything that you have on Earth. And so it's going to be hard to enforce them out there, but maybe all of that is going to take place here on Earth.
Yeah. How will space resources and their potential for enormous wealth generation benefit society in the broadest sense, rather than simply being a boon for corporations? You had mentioned that the resources are the property of all humankind. How would that work?
Yeah, that's a very, very tricky question. The treaties are very clear, and to change an international treaty takes a lot of time. And so what's happening now, the US just launched the Artemis Accords a few months ago, in which is saying, let's all play here by the rules. So if you come with us, then everybody, you know, starts having commercial operations and all that. But still, who's going to benefit from that other than the US, Russia, China, and all of those? What about other countries? And those discussions that are going on at The Hague, for example, you got developing countries saying, you know, what about us? And for the first time, we can actually be part of the space program, because we don't build rockets, but we have plenty of experience on mining here on Earth. We can teach NASA. NASA doesn't know anything about mining. They know about rockets. So these countries can have a say, but you know that they're going to be put aside by all the big companies. So they were even talking about, does it have to be a tax on things that happen on Earth so that everyone can benefit? Obviously, the big countries are saying, no, I'm not going to pay any money for doing what is so costly. So there's a lot of conversation of how you can benefit of that. Maybe you can make countries part of this effort and collaborate with other countries. I mean, if you're part of the US, you collaborate with the US. If you're part of China, somebody else would do that. But so that they can benefit. If not, this is going to be another Wild West, and it's going to be whoever gets there and extracts is going to win. The good thing is that the conversations are taking place right now. This is at the very start. It's not like on Earth that, you know, we just run through things and wiped out civilizations and we just did a lot of things. Here we're just starting. Hopefully we're going to do it right, but that's a very tricky question. It is not a tax. Maybe it's just enrolling people on the benefits of this. They're going to get benefit, because the moment you lower transportation costs, your telecommunication system will be lower. Whatever comes from there, if you ever bring material, they're going to lower the cost. So eventually they're going to be an impact, but maybe not at the very beginning.
That's what I have for prepared questions. With a small group like this, I think everybody is able to unmute themselves. If you have any questions, I think you can just unmute yourself and speak up.
Go. Yeah. This is Nate. Why do you think the Chinese decided to land on the dark side of the moon?
The Chinese are very aggressively not just going, they're developing a lot of the capabilities in space. You can see it now. You have rockets, they're putting together a space station, they have satellites. The reason they're going to the moon, it's mostly about resources, and they're very interested. They're saying it's for science, and they've landed there. But if you looked at where they landed, that's a key place where you have the most abundance of iron, of titanium, of rare earths, all sorts of things. So they're already looking for that. They're looking for helium-3. So they're very focused on doing this. And we know it, they have made it very clear, because the moment that they have the location, that they have the propellant, imagine what can happen. Once you have the propellant, instead of having all your satellites, spy satellites or commercial satellites, instead of letting them decay because they run out of fuel, now you can refuel them from space. You can move your assets very, very quickly. And so it's a very strategic point to be in. And so what we're seeing is sort of like a new race, very different from the one from the Soviet Union and the US. This is about permanence in space and using that for resources and to control the higher ground and everything else. So resources are going to be a very important part of this. So there's the economic, but there's also the strategic aspects, and it's happening. You can see it happening. They even launched last year the first prototype of a very small demonstration of beaming the energy from space to Earth. I mentioned that at the very beginning. That the country that makes that happen, if now you can beam energy from space and solve all your energy problems in just a few spots, that's going to be quite a winner. And they're really moving fast on that sense.
Achille, I was struck by one thing you didn't touch on, which I think the popular media is really fixated on, and I think the popular press believes that space mining or exploitation is going to put resources from space here on Earth. And of course, your talk didn't address any such thing, because I could imagine an asteroid taking out New York City if we tried to bring it down. But there was a popular article out maybe a year or two ago about an asteroid that was worth $1 gazillion in platinum group metals and such. And is that a realistic scenario, even in the distant future, or is that just something for popular press fodder?
That's a really, really, really good point. We have been organizing a meeting called the Space Resources Roundtable for 21 years now. Around 2012, two companies showed up and announced to the world, and they came here to Golden to talk about this, that they were going to do asteroid mining, that they were going after platinum and iridium and all those elements. And there was even, like you said, the first trillionaire will be made in space and all of that. From the very start, we have actually done economic analysis here at mines since 2000, and it never made sense to us. So we always thought, what is their business case? And they had a lot of money behind them. I mean, they have billionaires behind them. But after a few years, it was very clear that the business case went away, and they fade away because there was no real economic benefit of doing that. There's, like I said, there's plenty of platinum here on Earth, and it's going to be very expensive to bring in. And the moment you bring it, you're going to collapse the price because there's so much out there. I mean, this is real. An asteroid the size of School of Mines has more platinum, a metallic type, than has ever been mined and probably will be mined on Earth. I mean, there's plenty of it. But to go there and extract it and bring it here, the idea was to probably bring it closer to lunar orbit so you can go back and forth easy, but it's too expensive and it doesn't make sense right now. I mean, you will have to raise the price of platinum to levels that are extremely high to make this feasible. So that is why, and I'm not saying never, because you never know. I mean, maybe 50 years from now, like I said, the price is becoming so high because it's becoming so detrimental to the environment, or you're starting to dig extremely deep and it's become a problem. But right now, the use of resources in space is for use in space, not to bring them down here. The only thing that we can bring back, it's probably solar energy, some of the products made under low gravity, and maybe at some point helium-3 for fusion energy, maybe. But the problem there is that even though it's in much larger quantity, it's still in parts per billion. You're going to have to mine and move a lot of material to bring that helium-3 to Earth. So that case has not been made. It's all about how do you use it in space at this point.
Maybe it makes more sense to have a fusion plant on the moon and microwave it to Earth.
Yeah. And in fact, I mean, Jeff Bezos is of the opinion that at some point it will be great to move all industry outside, produce all the material there, remove all the mining, and just make the Earth a residential zone. That sounds great. It's just that at least I just don't see it in the next 40, 50 years. I may be wrong. It's really hard to predict anything, but that may be a little bit difficult. Yeah.
Thank you.
Mm-hmm.
Anybody else have a question?
Yeah, I do.
Go for it, Mary.
Yeah, I mean, I'm the person who belonged to the Planetary Society as far back as high school.
Mm-hmm.
Now, I was going to go to Mars.
Yes.
So this is right at my alley. Yeah, so thank you for a really interesting talk. actually. So I had a couple of really just specific questions. One regards the water that's in the craters at the poles, untouched by sunlight. And your premise is that all of that's been introduced by foreign entities, you know, asteroids, whatever, and collisions, dust. So first of all, is that correct? Yeah. And secondly, to extract that, I mean, if that is the case, then it seems to me you're going to have a fair amount of contaminants. I mean, really bizarre,
Yeah.
you know, contaminants. So what is the plan for that?
Okay. Yeah. The ways that water accumulated there, one is definitely probably ice, directly ice from the comets. The next one is asteroids. Asteroids contain a lot of hydrated minerals, and they ended up in those places. The other one is just every time that you have radiation from the sun hitting hydrated minerals, you reduce them. And so there's OH and water that comes out from there, and it tends to jump around, and then they get cold trapped there. So that's another mechanism in which you're getting water there. Very little of it. In fact, it's more in Mercury than on the moon that you get that type of activity happening because it's so close to the sun. So you have this water produced by radiation, and then it moves around and it gets cold trapped. But it's very little of it. So most of it probably accumulated billions of years ago. And the theory now is that while at first maybe it was nicely in the surface, as a result of so much bombardment, that has been churned and mixed around. So now you got regolith and you have ice, and you're gonna have to extract it. We've been doing experiments assuming you have a 4 to 5% water. The rest is regolith to make it as difficult as possible to extract it. And so that's the reality of that. In terms of what's there, as you saw from that list, there's also nasty stuff there. It's a lot of hydrogen sulfide, a lot that came from volcanic activity early in the lunar history. You got ammonia, you got mercury, you got magnesium. If you're going to drink that stuff, you're going to have to really clean it up. And there's some work in several places now on how do you do that. Maybe you heat it up and then start collecting at different temperatures, and then eventually you're going to have to clean it up to the point that you can drink it. And even to use it as fuel, it's going to have to be pretty clean. At the same time, you can start using those resources for something else. Sulfur may be used for concrete that you may do over there. Carbon may be used for methane and doing other things. So there's a lot of work right now on the cleaning up and the purification. At first, 5 years ago, it was, whoa, water, water, water. But now that we know that it's so dirty, there's a lot of work that's going to go on there.
Mm-hmm. Yeah. So I guess just pursuing water here, if you can just pull out that movie, The Martian.
Yeah.
You know, obviously, if people are going to do this with any kind of economic framework, the oxygen is super important, and also for cultivation of food, because you're not going to import your food.
Yes.
So I know this is a stretch for the moon, but has any thought gone into that?
Absolutely. In fact, somebody asked about, are we going to be fully independent of Earth? If we're going to have humans, the first thing you have to be independent of is food at some point. Now, that's going to require water, oxygen, but nitrogen. Nitrogen is extremely important here. And there's not much nitrogen on the moon except for the one that is being collected by the sun. But that content of ammonia that it's in permanently shadowed craters is very important. And so that's going to be needed for any type of food, of crop production there. And so that's going to be important, not only on the moon, but in Mars, that's for sure. Once you do that and you become independent of that, that's going to be important. Oxygen, there's some others, the Europeans are pursuing not the water. They're saying that's complex. We're pursuing oxygen that's just from the soil. So you got oxidized minerals, and by hydrogen reduction or carbothermal or heating it or fusing it, extract the oxygen and use it for breathing or for everything else without having to go to these very dark places. So there's a lot of work on doing that, mostly from ilmenite. Ilmenite is a mineral that has iron, titanium, and oxygen, and you can reduce it with hydrogen and get the oxygen out. And that's what they're pursuing at this point. And oxygen, it's important for humans, but like we do on the space station, a lot of it gets recycled. The water gets recycled, like 98% of that. These guys drink their pee and their sweat and all of those things. They're very resourceful. And that's going to be happening on the moon. So most of the water, even though you may think we're going to drink it all, there's going to be a lot of that recycled. And so most of the water will have to go to propellant and other activities on the moon.
Right. Mm-hmm. Okay, the final question.
Okay.
You know, back in the dark ages, when I was in graduate school in California, J.J. Pike from Stony Brook had a sabbatical, and I took some classes. Obviously, he actually was working on some of the original moon rocks, and my research, the project that I was working on was actually feldspathoids, and as you know, those are undersaturated and not uncommon on the moon, but pretty uncommon on Earth.
Mm-hmm.
So I guess from a research perspective, I don't know if anything actually came out of that. I mean, these were generally iron, magnesium bearing minerals, not necessarily our crust forming minerals in any abundance. And do you have any idea if anything came out of that research in terms of resources?
Mm-hmm. I don't know about specifically that type of research, but a lot has come out from looking at the lunar rocks and trying to determine their content. In terms of volatiles, there were some leaks on the boxes that they use, and so those went away. Some boxes have not been opened. They're just being opened right now.
Yeah, I know they still have some of it available.
Yeah, absolutely. Yeah. But now with this big commercial push to get to the moon, I mean, you're going to start seeing landings on the moon in 2 years like you wouldn't believe. I mean, there's like 13 companies doing this, and NASA's even paying for companies to bring material and rocks and dust. And so there's going to be a lot more coming, and hopefully we'll learn more from that material, because we only have it from the equatorial regions. We don't have it. There's only one from the highlands, but we need more from the lunar regions to see how that the type of minerals there and all that. So a lot was learned from the 380 kilograms from Apollo, but there's still more to be done. Yeah.
Mm-hmm. Thanks.
Is that you, Geller? Oh my gosh.
I think so. I think so.
Oh my God, my heart is rejoicing. That guy knows more. I learned from that guy, geology from that guy, more than anybody else in the world.
Angel, you're the best.
He gave me access to all the rocks and minerals, and we both work on bringing a rock from Apollo 15. I miss you so much, Bruce, that you wouldn't believe. I have to say it in front of the group, but that's I have to say it.
You're a great man.
I still have serpentine from you. I still have all sorts of things. So I learned a lot. That geology museum, it's wonderful, and Bruce really spiced it up to the point that I enjoy going there every day.
Thank you very much.
Great seeing you, Bruce.
All right. Well, thank you very much for joining us, Angel.
Oh, it was a pleasure. It was a pleasure. Always good to be in touch with the people that actually do the work here on Earth, because whenever we talk to NASA, for them it's like, oh, there's water. Now we have everything. Yeah, but do you really? And then we start talking proven reserves and all of that. Is that what is that? Well, you're gonna have to drill a few holes to make sure that that thing is there. Where is it? How we can get to it? Oh, really? Yeah. You're gonna have to do a lot, and so that's why this community has a lot to offer. And we've been bringing the USGS to talk to them, and we've been bringing the people that are on the field, exploration geologists, economy geology, everybody, just to let them know what it takes to do this. When they say there's platinum, yeah, but in what type of mineral? It's very different if you're going to extract it from one or the other. So they need to learn those things from a community like yours. And so we may be calling you. Your call may be to the stars, not just here on Earth.
Yeah, one question.
Yes, Jane.
This makes me think that maybe something like drones would be used to explore the surface, are there other ways to do it besides remote sensing?
Unfortunately, drones cannot be used because there's no atmosphere, so there's no lift. But satellites and small, what's called CubeSats, very small satellites are going out actually next year to get as close as possible to the surface, remote sensing. But then the idea is just impact those. If you can have balls, relatively expensive with spectrometers and to ways to measure, if you can impact probably 100 of them in an area, you can determine at least the composition of ice, how deep it is, and get a feel of exploration by doing those impacts. And instead of having these multi-million rovers that are moving around, that it's really hard. You're going to have to do something more inexpensive and get the information, as much as possible. I mean, as geologists that you are, you would like to drill every 15 feet or so. That's going to be very hard on the moon. So you're just going to have to get as much information from impacts from little rovers or other type of things. But yeah, there's Mars is a different thing. You can have some drones there, and there's actually one on this mission that is going to Mars. So be on the lookout next year. There's going to be a helicopter on Mars, so that's going to be a nice thing to see.
Are you principally using shortwave IR?
Shortwave?
Infrared?
Yes, there's all sorts of things, mostly infrared. Yes, that's what's been used for mineral observation. Yeah, that's mostly it. There's some neutron spectrometry just for hydrogen, but for minerals, yes, you're absolutely right.
All right. Well, if that's it,
okay,
I think we'll close her down.
Thank you so much. It was a pleasure, and I'll expect to be in touch with you.
Thank you. Very good talk. Excellent.
Bye. Thank you.
Bye-bye.
Thank you.
Thank you.
Bye. Bye, Bruce.
All right.
Thank you.
Have a good one. Bye, Mary. Good questions.
Bye.
Okay, bye.